Okay, that quiz was A's number of letters in your first name, B's number of letters in your whole name, C's the total number of letters, which is of course the same as B in this case. Okay. F of t is t squared plus c, just and your integrals that you do in this class, mostly pretty simple integrals, okay? And derivatives. Average value of f of t on the interval from A to B, and that's what I asked for. And I drew this picture here to kind of give you something. I didn't write this formula because that's what I wanted you to have when you come into class. Okay. If I do this, so here's A. So at this point, y would equal f of A, right? There's f of A, right? Make sure we understand that. At this point, y would be f of B. Okay. Now, if I draw a straight line from here to here, it comes out a little higher than that curve, doesn't it? Okay. But in terms of A, B, f of A, and f of B, can you tell me what the area of that thing is? Let's just so first of all, how far is this? Well, that's B minus A, isn't it? So here we have B minus A. Here we have this height, which is f of B. This height, which is, I'm sorry, that's f of A. That's about a better fix it. Okay. So what's the area of that? The area, well, I'm going to say this. If I draw a dotted line down the middle, the average height of this thing, if you want to regard this as a base and a height, is right here, isn't it? Actually, I should be a little further to the right, but we'll pretend that's in the middle. Okay. So pretend this is the midpoint. I kind of messed up. So if I go a horizontal line through the point here at the midpoint, I get this. And this has the same area as the original shape. Why? Because this triangle is similar to this one, because this is a straight line. Okay. It's something I want you to understand because it's going to be applicable at various points throughout the course. All right. So be sure you review this. It's not totally clear to you. Review it anyway. Take notes if you want to. So what are the dimensions of this? Well, this midpoint height is halfway between this and this, isn't it? That makes sense? Just by simple geometry, which nobody ever studies very deeply because they try to teach it to everybody as eighth graders, and nobody learns much. Okay, so you really want to kind of think through the geometry, similar triangles and rectangles and all that stuff. But by the geometry, since these are similar triangles, and since this is a straight line, you put all that together and you figure out that this is halfway between this and this. So halfway between f of A and f of B is add them together and divide by 2. That's how you get the number halfway between two numbers, which ought to be second nature, I think, probably is. Okay. If it's not, make sure you think it through. And this is B minus A. So the area is leave myself room to write it. So it's written too small to see, but it's this times this, right? Now, you plug your numbers into this, and take your calculator and plug the numbers that you got from your integral. You got to get the same thing. Yes or no? How many think yes? How many think no?
I think yes.
Was that a yes or no? So yes? Okay, well, answer is no, because this thing's curved down below this, and this area under this thing is less than the area of this thing, and the area under this thing is what's represented, is represented by the integral. Okay? So this is an overestimate of the area, which is an overestimate of the integral. Although on this interval, maybe it's close, maybe it's not. Depends on how much of the parabola you cut off. Okay, if I cut it off from here up to here, there's going to be a lot of parabola way lower. Okay, so I'm going to ask you to check that out. And get it to me for next class. Okay, which is, of course, a week before that, before you forget. Okay, and the way you get that to me is just write it out on a piece of paper, take a picture of it, and send it to me. Fair enough? I don't want to take your paper away from you. I hate to take this one away. It won't hurt you to rework your integral. Use your calc. You can use Wolfram to do that integral if you want to, since you've done the details here. Okay? Fair enough? So it shouldn't take you more than a few minutes. And then you got a formula here you just plug in. You can use Wolfram to evaluate that one as far as I'm concerned. Although I kind of recommend you do it by hand because it's not going to be that bad. Okay? You can use your judgment on that. You reinforce a lot by actually doing the calculations by hand. It sometimes gets ridiculous. Like it would be ridiculous to cube 783 by hand. Okay? It's not ridiculous to do 3 to the 4th power. Well, the other thing I'm going to say about average value of a function, which I think is a real important concept that people do not bring out of calculus for your calculus. I thought a little more deeply about first year calculus than most students did. So they made better grades than I did, but I understood it better than they did. Then by second year, third and fourth semester calculus, I kind of did real well because I thought through what was going on in first semester calculus. I think the tests were over the superficial stuff. I was kind of stupid about the superficial stuff until I got it. My point is, this is an important concept. And even though I thought deeply about it, I just vaguely remembered it. I did remember the formula. Then I thought about it and said, oh, that's what it means. That was in my second grade. Okay. So what's it mean? Get it out. Okay. There is a straight line I want, but I'm talking while I'm supposed to be thinking, and you never know. Let's say I want the average value between here and here. How am I going to find that? Assuming I got a graph and I got labels, and I want to just estimate it because I don't want to go to the trouble of doing the integral. Okay, then maybe all I've got is a graph of data, where I've got a curve that I think fits it, and I'm trying to figure out my average value. A couple of ways to do it. One, you could estimate the value of this thing at 10 different points equally spaced, and then average those 10. That would work, wouldn't it? Give you a reasonable estimate of your average. Just sample 10 equally spaced points, and you get a pretty good estimate of the average. A graphical way to get a pretty good estimate of the average is say, I think the average ought to be about here. Well, that's not a good estimate. First place, the line isn't even horizontal. But, okay. The reason the average value is here is that the part of the curve that you're leaving out, or that that's included under the curve, is way smaller than the average value that's included under this line, or than the values included under this line. These areas would have to be equal in order for this to be an average value, because then the area under the average value line would be equal to the area under the curve, right? That makes sense? So my line needs to be somewhat lower. Well, I'm going to let it be sloppy. Since I'm smudging stuff out, well, I'm not going to have to smudge that up. I need to smudge this out. Kind of smudge most of that line out. And I'm going to try a better line, maybe down about here. Is that better? Well, I've got this area here that's under the curve. And I've got this area here that's under the straight line, but not under the curve. Well, this area is a little bigger than this area, so I probably have to go a tad bit lower. Make sense? But once I get the line that excludes as much area as it includes, excludes as much area under the curve as area above the curve that's excluded. He said that right. You understand what I mean? Okay. You want these areas to be equal. Then you have a good estimate of your average value. And if you sketched a graph of your function here and printed it out, put a line across it, I bet your line would be pretty close to your average value. Okay. So what I'm going to say is another thing I want you to do is I want you to sketch the curve. Now, when I say sketch the curve, I mean use software of some kind to give you a good picture of the curve and then do your best facsimile. Make sense? Sketch your best estimate of the curve. I wouldn't go to the trouble of printing it out and so forth, because we're just approximating and getting the idea of an average value. Okay? That makes sense? I'll try to write it out for you when I post the videos this afternoon. All right. Now, one reason you might want to do this. How many of you have heard of Newton's second law? Okay. It ought to be in middle school science. But it can't be because we're trying to aim thing at IQ 80. So everybody can pass. Well, Newton's second law says, let's just say I've got, well, so I've got this card here. Okay, this card's got heart and everything on it, might weigh close to 100 pounds. We'll say 40 kilograms. Okay. Give us something through there. Now, unfortunately, you can't see this online, but I've got a cart. It's about this high. It's got 3 shelves on it. It's got 2 boxes. Each box probably has about 30 pounds of papers in it. Cart itself probably weighs 40 pounds, 50 pounds. So I'm saying it's close to 100 pounds. And I'm going to say 50 kilograms then. How do people know how many pounds a kilogram mass would weigh? How many pounds per kilogram? Okay. It's easy to learn. It would be a much better advantage. If you know that it's applied a few times. Still, it's not going to give you that much trouble. It's 2.204, I think. Okay. So what do I have to do to speed this thing up? I've got to exert force. Okay. So let's see how. I'm only going to speed it up for about. I don't even want to speed it up for 2 meters. I'm not going to speed it up very fast because if I did, I might lose control of it and take out that wall or something. Okay, ready? Here we go. Okay. How fast is that going when I let loose of it? We've got a foot per second, more than a foot per second. 7,001. How far do you think it went? Show me some hands. Want me to do it again? I'm gonna do it again. Then I'll be exhausted, won't be able to do it. Okay. Okay, we're gonna let loose more or less than a foot.
About a foot.
About a foot. Show me with your hands how far you think it went. Okay, I'm saying anything from 1 feet to 2 feet. Right. So I'm gonna say half a meter. Okay, well, if that went half a meter, how long did it take me to get up to that speed? An hour? Less than an hour. What part of an hour? No. Okay. More than a second? More than 5 seconds? 2 seconds? I see 1 second, I see 2 seconds. Let's say half a meter per second and a second and a half. Now this is a calculation. I want you to go over this. I want you to remember this calculation. We haven't developed the theory of it, but we're very close to doing that. We probably will by the end of the day. I just realized I pushed something with this arm. They mentioned what happened to this arm. Yeah, yeah, it's good that I could push something. Not, I mean, I felt a little something, but didn't really get my attention. Of course, now my arm aches. No, it's okay. All right, so I pushed 50 kilograms breast to 0.5 meters per second in 1.5 seconds. Okay. Now, my question, just in vernacular, if you know calculus, if you know pre-calculus, you should be able to answer this question. You got to deconstruct it a little bit, so if you can't answer it, you're okay with it. I'll give you a minute to think about it. At what average rate did velocity change with respect to time? What do you think? We're going to discuss it for a minute, so I'm going to pause the recording. Okay, now I observe that nobody knows what the definition of an average rate is, or the idea of an average rate, or why calculus was all about average rates and average values. Okay, because that's what it's about. And you prove things. You take a limit to find a derivative, you're finding a limit of an average rate. So you get an instantaneous rate, average rate of change of y with respect to x. And that's how you interpret a derivative, and that's the meaning of the derivatives that you're going to see in some of the physics, okay? In fact, you're going to see it in stuff right now. And it's not hard. It's just kind of a revelation. So, oh, that's what all that meant. That's why we did all that, okay? There are reasons. And important ideas. So I'm going to get a little more formal in the way I write these things out. That makes sense. The average rate is a change in this divided by change in that. But I want you to get the mathematical definition. And maybe a couple of mathematical definitions and think about it, okay? But you agree that the velocity changed by 0.5 meters per second in 1.5 seconds, right? Now, if you earn $50 in 3 hours, Get what radiator money? That's dollars per hour. You can figure that out instantly because that's something to think about. Okay. Travel 300 miles in 5 hours. What's your average speed? Boom, 60 miles an hour. That's a 300 miles divided by 5 hours, 60 miles per hour. 1.5 meter per second change in velocity, or 0.5 meter per second change in velocity. 1.5 seconds is a third of a meter per second every second, right? So there it is. And you can think of a third of a meter per second per second. Now, I admit, for some reason, these unit things, even though I had an outstanding background in trig and logic and algebra and all that stuff, I do everything that I need to do in those courses, okay? I hadn't had pre-calculus, I had some deficiencies, which caused me a little bit of problem in my first couple of calculus courses. But, you know, I was pretty well prepared other than that. But the whole meter per second over second, I had to keep reminding myself how those units worked. So I'm just going to write it out for you. That means meters per second over seconds is meters over seconds times reciprocal seconds, which is meters over seconds squared. Okay? That makes sense? That's just rules of fractions. Now, if I'd have thought about it that simply, I was thinking about it more complicated. I was overcomplicated it. And you're going to overcomplicate things. Believe me, I understand. I did a lot of that in my freshman year. Started to get over it my sophomore year and was pretty much over it after that. Okay, anyhow, you think of this as meter per second though, because that's another. If this was dollars and this was seconds, you know that was dollars per second, right? So this is meters per second over seconds. That's meters per second per second. That means every second you're changing by 1/3 of a meter per second. You're picking up a third of a meter per second every second. Okay. And once you digest everything I'm telling you here, it'll be much to your advantage. Things will be much easier for you. Okay. I've garbled that word, but it's velocity. Acceleration is rate of change of velocity. Average acceleration is the average rate of change of velocity. Now put WRT T for with respect to time. And the reason we want to do that with respect to time is I could also figure the average rate of change of velocity with respect to distance. Okay, well, the cart was right there. What was the rate of change of velocity with respect to distance? You take the change in the velocity over a short distance and divide that by the distance. You get the rate of change of velocity with respect to distance, right? And you got a chain rule that relates the two things. dv dt equals dv dx times dx dt, okay? Simple chain rule. You might ponder that, but it'll come up again. Okay. It's important for the distinction between impulse, momentum, and work energy. And that's something we'll get to for too long, but we'll worry about it when we get there. Okay, so average acceleration is this. So what I just calculated here is average acceleration, isn't it? It's the average acceleration for that time interval, for that 1.5 second time interval, right? So all that makes sense? At least halfway. We pushed the thing. It went from 0 to 0.5 meter per second in 1.5 seconds. That was about 1/3 of a meter per second. Okay. So that was the average rate of change of velocity for that 1.5 seconds, which means that was the average acceleration. Now, I'll guarantee you the acceleration was not uniform. I wasn't trying to make it uniform, and then if I had been trying, I wouldn't have been able to. If I practiced a lot with a motion detector, I could probably get to the point where or if I could, just by feel, keep exerting the same force, which is difficult to do as you're speeding up. There's very little that we do where we exert a uniform force over a distance, okay? It's very unfamiliar, very unnatural. If I am lifting a weight, okay, the speed of the weight changes. Now, if I lift a weight at a constant speed, then I am pretty much exerting a constant force, okay? With the arm as it is, I think I could probably lift 8 pounds. Hopefully I'll get up to 800 shortly, but I think it might be a permanent limitation. And I'm at the age where those things happen. Okay. Probably a little bit of rotator cuff injury, not real bad. But I don't want to make it worse. Okay, well, the point is, that's an example where you might be, but if you're trying to lift a heavy weight, you don't lift it at a constant velocity. If you lift weights, you know that. And if you don't know that and you lift weights, watch it next time. But don't do it with a really heavy weight, because while you're watching it, you're probably not going to lift quite as efficiently as you did, and you might drop that weight on your throat or something. So don't do that. I'm just saying, think about, what does it feel like to move something at a straight, at a uniform velocity? If you're throwing a football, all kinds of changes in velocity, all kinds of changes in the force that you can exert at different points, many different things. All right. Well, you're actually getting some physics here. So we could say that instantaneous acceleration, that's just a limit as you take change in velocity over change in time for shorter and shorter time interval. That's just time derivative of velocity, right? And if we understand that t is the variable, we could write that as v prime of t. If I write v prime of t, implicitly, t is the variable with which we're taking the derivative. I mean, in this case, velocity is also changing the position. If the position is x, you could also have a v prime of x, right? But if we write v prime of t, we mean dv dt, okay? But to be totally unambiguous, we use this notation. There are reasons for these notations. Okay, that's your definition of acceleration. Okay. We could let x push that thing in pretty much a straight line. Okay. So we could let x go from 0 to 1.5 meters. We could plot a graph of speed versus x, right? Or x versus t. Well, it's the x versus t that we want. And that's just a derivative. Now, x would be your, in this case, your position in meters, so that the derivative would be a change in velocity, which is going to be in meters per second, divided by a change in time, which is in seconds. And that's an example of such a calculation. Okay? All that makes sense? Now I'm going to jump to something that you're not really going to be responsible for a little while, at least a week or two. Net force equals mass times acceleration. Okay, that's Newton's second law. You might have seen the equation without knowing what it's called, which means you're missing a whole lot of important historical perspective. How did Newton figure that out? Pretty deep. He figured it out by watching the moon. And apocryphally, the story is that Apple hit him in the head while he was thinking about the orbit of the moon. Okay. Realized that the moon was subject to the same forces that the apple was. And everything else is basis of most Western civilization as far as technological. I didn't say that real well, but I think you get the idea. Okay, so we have this. And the reason I want to have this is that card has a constant mass. So in this case, the net force that was being exerted, and that net force was not the force that I was exerting. I was exerting a force, but there was some friction resisting me. So if I was exerting 20 pounds of force and friction was exerting 5 pounds of force, the net force would have been what? 15 pounds. Because friction was exerting force in direction opposite of my push. So that's why we put a net on the force. Make sense? So in this case, the net force is 50 kilograms times 1/3 meter per second squared. What unit do we get? We multiply a kilogram by a meter per second squared. We get a kilogram meter per second squared. Maybe a little dot between kilogram and meter. Since we got 2 letters in kilogram, KGM might, I don't know. MGM is Metro Golden Mayer, KGM might be Cooper Golden Mayer, Meyer movie studio. Okay, and that's not what we're talking about, kilogram time meter per second. And a definition I want you to remember, so you don't have to worry about remember it. That's 16 2/3 Newton. Newton. I don't have room for an S, but I'll kind of slip one in there. All right, makes sense? Well, I'm telling you way more than I intended to, but since we're here, I might as well tell you. We've got a graph of force versus position. Okay. Now, if my actual force probably was decreasing a little bit, say it looks like this. Position is 1.5 meters when we stopped. Then I stopped exerting a force. Between 0 and 1.5 meters, work net work is the integral of the net force with respect to X. What aspect of this graph then would be the net work? Stop and discuss this for a minute. Okay, I took it a while. A couple of little questions and answers before somebody came up, well, okay, the integral is represented by the area under the curve. That should be a no-brainer. Go back to the proof of the fundamental theorem of calculus or the definition of an integral in terms of Riemann sums. If you don't know how that's proved, you really ought to review it. We've learned to do some symbols. In calculus, we learned a lot, but you maybe didn't learn what it really means. And you need to know what it really means in order to apply it to physics, in order to understand a lot of the physics. Okay, so the net work is this. Okay, so this area is your work. Okay. Another important thing about work, and you take a note of this. I'm giving you an overview of a whole lot of stuff that we're going to develop over several weeks. But having an overview and understanding it in terms of a simple example and in terms of the necessity of understanding certain aspects of calculus that people generally come out of the first year not understanding. Okay. And it's always been so. It's not just recently. And there's no deficiencies in the course that you were taught. I know who taught it. I know how he teaches it. And it's an outstanding course, but you didn't take out everything you could have. Okay. So you need to go back to what you learned there and put it together. Okay. Anyhow, there's your force. There's your work. It's the integral under the curve. And Work is a change in kinetic energy. There should be a net under it. You can't read it, but there it is. Okay. And remember, remember the formula for kinetic energy? I wrote it down last time, should have reviewed it. Should be locked in. Everything I'm doing here needs to be locked in next week. Okay? Everything we've done, and then you're in shape. Start doing some pretty good stuff. Okay, and learning the physics faster and more efficiently and more effectively. Why is kinetic energy 1/2 mv squared? Because the work is the integral of the force with respect to distance. We'll see why that is. Okay. So one more picture I'm going to squeeze in here. Now, I don't know what my initial or final force is, but I know that my average force, 16 1/3 newtons, 62 thirds newtons. Okay. Which means that if I draw a line for my average force, I'll say it's approximately equal to 17 newtons, just rounding that 16 2/3 up. Because the area that I have under the straight line, but not the curve, is pretty close to the area that's under the curve, but above the straight line. Line should be a little higher. There's a picture of my average force, though. Rough picture. Okay. And all this is really to illustrate in terms of some pretty basic physics that you're going to be learning, giving you a preview of that physics related to the fact that the average value of function is the integral divided by the interval. Okay. Also, we mentioned the fact that the derivative is the limit of the change in this divided by the change in that. That's what a derivative is telling you. Derivative is the rate of change. The integrals that we do in the course are not difficult. Y'all were able to do the integrals last time. Okay. Now, if I ask you to integrate the sine of pi t, you might have to do substitution. Or take a derivative of the sine of pi t, you might have to use a chain rule. It is simple substitution or simple chain rule. And we don't go much beyond that with calculus. I might mention things that go beyond that in case you're interested. Okay. But I'm not going to spend a lot of time on it because we need to spend time on valid content of the course. Now, I'm going to switch gears, but all that comes out of average value, but we went way beyond just the idea of average value. Okay. I want you to draw on a piece of paper. Just don't have to have this in, just a little quick paper. I don't want to see what you draw. Just a square that you know is 10 units by 10 units. Now, here's an arrow representing vector A. And here's an arrow representing vector B. Can you draw me a sketch of the sum of these two arrows, starting at your lower left as the initial point of A? So this point would be here, and it would go here. Can you draw me a sketch of A plus B? Just saying, yeah, I'm just kind of probing to see what you know about vectors. If you know quite a bit, but we find that vectors are mostly studied in pre-calculus, and it comes near the end of the spring semester and often gets, if not left out completely, done in a very incomplete way. And people come out of the course where they're supposed to learn about vectors not knowing. However, most of you have had linear algebra, so you really ought to know that. Okay, looks pretty good for the most part, but let's just work it out. Here's my vector A. Now, I guess I better redraw this because I try to label it. If n, actually A is not this symbol. So there's A. I'm just going to deal with A to start with. To get to A, assuming this is your X direction, and this is your Y direction, we can go this far in the Y direction and this far in the X direction, right? So these are your components. These are components A sub X, sorry, A sub Y, and A sub X. A sub Y, if this is 10, this looks like maybe it's 3. Now your picture might be different. I didn't see any numbers that looked ridiculous from anybody that had 2 components. AX looks like it might be what the heck, 4.5. Okay. And then if this is B, well, we could have a BY and a BX. And it looks like BY is about -4. And BY, or that's BY, and BX looks like about -1. Comment. And I'll say it, but I'll say it kind of fast. You might want to review the transcript if you're not sure of it, or review this part of the video. But I want you to master everything we talk about in this video. Okay. So I won't say angle, I'll say the direction of A. It's the arc tangent of AY over AX. Because, if I draw A here, this is theta, then AY is the opposite side, and AX is the adjacent side, and the tangent is opposite over adjacent. For the y over the x if you're using a unit circle definition. And the 2/3, which or you can estimate it, be about 2/3. I don't want to do that. I don't want to take the time. And the magnitude of A is the Pythagorean theorem. So, hypotenuse of a right triangle besides AX and AY. So without labeling all this, here's how you calculate it. And you do the same thing with B. Make sense? Familiar? Not familiar, you need a pretty good review of at least right angle trigonometry. We don't use a whole lot of
Right next door.
law of sines and law of cosines, not at all first semester. Okay. But you're supposed to know that. It's supposed to be part of your pre-calculus class. We do. No, doesn't matter. All the stuff in the first chapter. It's not the first chapter, find it where it is. And I never look at it. Except to figure out what's what. And given all the pandemonium, I haven't had a chance to look at it. Should have, but looked at a lot of stuff, but not that. Okay. So you need to know that much trigonometry. Do you know the definition? You have the dot product. I mean, you could write down the definition of the dot product. And you've had it drilled into you last spring, so you can't live without it, you know. Is it important? You advise everybody to nail it right now. It's supposed to be part of your pre-calculus. Okay. Now, if you got your right angle trig and your obtuse angle trig and didn't get to the dot product, it's not a major tragedy because if you know all that stuff, it's really easy. Dot product is very easy. Okay. Its definition is the magnitude of A. And of course, if you had linear algebra, you should have used the dot product quite a bit. I mean, did projections and stuff like that. But anyhow, it's A dot magnitude of A, magnitude of B times cosine of the angle between them. Okay. And if you know the components of A and B, it's just you probably didn't see it written out this way, but it's just product of your X components plus a product of your Y components. And I'll use that notation because it's consistent with what I've already written. Okay. So you could make good estimates of the components of B, right? And you could calculate that dot product based on your estimates. And once you know what the dot product is and know how long A and B are, which you can calculate from this, you can calculate the angle. If you know the only thing you don't know is cosine theta, and then take the inverse cosine and get the angle. So I said it. Read the transcript, watch the video, but I want you to do that for the next time, just based on your estimates. Nothing more precise than that. Also, I want you to read that first chapter. And we're out of time, so I'll double check the first chapter. And if it's not the first chapter, I'll let you know in the assignments page, okay? And I'll be posting that. Hopefully within the next hour.